16 million Australians choose to live in the driest inhabited continent on Earth, a land that also boasts the world's most unpredictable climate. Out here in Central Australia, we see plants and animals pushed to the limits of survival. The arid zone covers more than 70% of the continent, and much of that vast area receives less than 200 millimetres of rain per year.
Today, thanks to decades of innovative research, we understand a great deal about the ecology of arid Australia, which is fortunate because the clear message from all of that research is that the Australian environment is in severe ecological crisis. The arid zone is expanding. The country is turning literally to sand.
It's no small irony that the very same sand yields silicon, the material at the heart of computers that hold the key to Australia's future. Over millions of years, the Australian landscape has undergone profound changes. All of this desert once was blanketed with lush, diverse rainforest. That rainforest has now retreated to tiny fragments clustered along Australia's east coast, mainly because of changes in climate over the past 30 million years. Changes like these are very much a part of life on Earth. But in recent years, the pace of change has begun to accelerate alarmingly as people have systematically cleared forests and put the land under the plough. In our desperate race to increase productivity, we've pushed this country very hard indeed. Over 200 years, we've removed 50 billion trees. Irrigated vast areas of semi-arid land, and we've dusted millions of tonnes of fertiliser across the landscape. 1,000 billion tonnes of salt are poisoning the soils of the Murray-Darling Basin, costing Australia $100 million a year in lost farm production. But the story's not all gloom and doom. Thanks to the miracle of satellite technology, we can plot changes in the Australian landscape on a daily, even hourly basis. We can see the colour of the country change as the plants bloom after the rains, and we can chart the impact of fires, floods and frosts. This sequence of computer-enhanced satellite pictures, shown here for the first time in animated form, charts the Australian continent over a 5-year period. The sequence shows clearly how the vegetation flourishes each spring and emphasises graphically how dependent the country is on its rainfall. By analysing how these images change with time, scientists are discovering patterns in the landscape. Patterns that will help us predict the consequences of our actions, both in terms of their impact on the environment and ultimately on the economics of our enterprises.
This is a revolutionary time. For the first time ever, Australian ecology is starting to make sense. The puzzle really is coming together. And as in all good science, the picture that's emerging is unexpected and surprising, as we'll see when we take a fresh look at the ecology of rainforests and coral reefs.
The computer revolution in understanding the Australian environment came of age when it became necessary to map the whole of the Great Barrier Reef. Sometimes referred to as the world's largest living thing, Australia's Great Barrier Reef boasts the highest diversity of animal species of any marine ecosystem on Earth. Often touted as a perfect example of nature in balance and harmony, the Great Barrier Reef is in reality a battleground, with creatures everywhere struggling to claim and secure territory. Recent research has revealed a new and surprising view of how the reef operates. According to the new view, the extraordinary variety of life on the reef has less to do with harmony and balance than with a system in the early stages of recovery from catastrophe. The reef is continually being devastated by physical forces like storms and cyclones, and by its own occasional biological excesses, like outbreaks of the crown-of-thorns starfish. In all biological systems, it turns out that high diversity is typical of a group of animals or plants trying to get established, usually in the wake of some disaster. If the reef could be left alone for long enough, it would probably settle down to a more stable and certainly less complex community. The Great Barrier Reef covers almost 350,000 square kilometres and includes 2,500 individual reefs. In 1975, a grand plan came into being, the creation of a vast multi-use marine park that was to encompass the entire Great Barrier Reef. In order to develop a management strategy, there was an urgent need for accurate high-resolution maps of the entire reef system. But no such maps existed, and it was estimated that to map the reef in detail would take 10 years and $20 million. Thanks to a little computing sleight of hand, it proved possible to extract the mapping information from pictures already being captured by the Landsat satellites. The software package was called BRIAN, jargon for Barrier Reef Image Analysis. Remarkably, this high-tech modelling can now be run on small, relatively inexpensive personal computers, using a software package called what else but MicroBrian. These enhanced satellite pictures reveal things like the depth of water in a lagoon, what kind of algae grow there, and whether an area is likely to be unusually susceptible to pollutants. By the mid-1980s, the stage was set for a genuine revolution in information exchange that was to become the most significant advance in the history of environmental research. Possibly the friendliest interaction between science and the general community since the Industrial Revolution. And the microbrine approach didn't stop with barrier reef mapping. Because the system is relatively cheap and immensely powerful, it's now used in a wide range of management applications, including farm management, fire prevention, and fisheries research. Here in Townsville, the Great Barrier Reef Marine Park Authority has achieved a remarkable feat. They've built the world's largest artificial coral reef, a project that could not have succeeded without a great deal of basic research on coral biology. It's a spectacular example of what all this increased knowledge can mean for the person in the street. As with a natural reef, one of the greatest problems is to keep the seawater as pure as possible. Even rainwater contains far more nutrients than the water in which I'm swimming, and if a diver was to urinate in the tank, the nitrogen content of the tank water would more than double, and that would be disastrous for the corals. It would also be displayed on the nitrogen analyzers for the aquarium staff to see. As researchers have come to a better understanding of the reef and its inhabitants, they've been able to advise the Marine Park Authority on the health of the reef and to warn of trouble spots caused by human activities. As the artificial reef demonstrates so clearly, corals can only grow in extremely pure seawater. Fortunately, the waters that bathe Australia's east coast are pure. They're exceptionally low in nutrients. That's one reason the ill-fated tourist road through the Daintree rainforest was such a disaster. Despite the fact that remote sensing data showed clearly that it would have been cheaper and more permanent to put the road behind the rainforest, the road was carved right through the forest along the coast. As researchers had warned, the first heavy rains washed the road away, and the flood of nutrients in the runoff contributed to the death of nearby coral reefs. The terrestrial equivalents of the Great Barrier Reef are the tropical rainforests. Tropical rainforests are the most diverse assemblages of plants on Earth. In just 2 hectares of this forest in far north Queensland can be found more than 150 different species of trees, more than the entire tree flora of Europe or North America. As in the case of the Great Barrier Reef, this remarkably high diversity is also the result of frequent disturbance by storms and cyclones. This walkway, which reaches 30 metres into the treetops at O'Reilly's famous guest house in the Lamington Plateau near Brisbane, offers a rare treat for tourists. There are few places in the world where people can get such a splendid bird's-eye view of life in the rainforest canopy. And it's the kind of tourist attraction that does very little damage to the forest. These trees are so tall that normally it's very difficult to get up into the canopy to see what's going on. But if you climb onto a walkway like this, we can see that it's really a battleground. There are plants of all different sorts vying for territory, trying to compete for those vital resources of nutrients and light. Hidden within this fern is a young strangler fig. It seems innocent enough now, but within 100 years it will have outgrown its host tree, progressively throttling it until just the strangler remains, like this one. No matter whether you're a casual observer or a professional botanist, rainforests like these dazzle you with their complexity. Everywhere you look, there's a new and unrecognisable plant. In such a complex system, how can we predict the outcome of natural disturbances like cyclones or man-made ones like logging? The answer comes from people who know these trees like old friends. Scientists who aren't afraid to get down on their hands and knees and crawl through the mud and the thorns and the leeches. Dr. Ian Noble from the Australian National University leads a team of researchers seeking to understand the fine detail of Australian ecology. Their approach draws on a wide range of environmental data, including satellite imagery, but they're trying to take it a stage further, to develop accurate computer models of entire ecosystems, in the hope that when management decisions are required, they can be based not on emotional arguments, but on facts.
If we measure enough individual seedlings like this one and keep on coming back, we gradually build up a picture of what's happening in this forest through time. But there are a lot of these seedlings. For example, we've got over 100,000 readings just from this patch of forest alone. And to handle data like that, you really need a computer. Well, here we have a rainforest growing on a computer screen. We've got a computer model running which is mimicking what happens in that patch of rainforest that we've just been looking at. It shows different species of trees shown by different shapes and different colours. And we see the years clicking away here, the trees growing each year, and every so often you'll see a tree dying on the screen. Now, let's imagine the worst possible event that might happen to this forest in nature. Now we can go out and try that on the screen without having to wait for it to happen. And let's try a cyclone, very bad cyclone. So we'll apply it now and watch the result. The larger trees die. They were killed, knocked over in the storm. A lot of the smaller trees were killed as well. And now we're seeing the forest regrowing in this patch. And you'll notice some differences in the forest. If you watch carefully, you'll see there's a lot of these trees shown by brown triangles. They're trees which like the light that's been created on the forest floor, like the stinging tree. And you can see that they're growing very rapidly and they're really dominating the plot at the moment. Some people have argued that logging is just another disturbance like cyclones. Now we can use the model to test out some of these ideas, and we can try various logging practices and compare them with the impacts of a cyclone. Now let's just try that here. If we try a logging process now, it should come through. Now they'll take the larger trees, but only trees of certain species. See, some large trees were left in this logging operation, so that even though it's created gaps in the forest and it's created some disturbance on the ground, we see the same sorts of things happening. There's the light-loving trees coming through, like the stinging tree, but the situation is different. We still have a couple of large trees dominating the site. Now, of course, we can try other treatments, other logging methods. It's possible to have a logging prescription which says that some of these larger trees should be removed at the same time. But the value of the models, of course, is that we can try all of these out on the computer, get some idea about how much effect this might have before we need to go and test them in the field, which is much more expensive, of course.
This is tropical rainforest in far north Queensland. Nearby at Tully, an incredible 4.3 metres of rain dumps down during the summer wet season. It's the wettest place in Australia. All of that water is essential to maintain the lush forest, but that's about all the forest needs. Like the barrier reef, a tropical rainforest is a closed ecosystem. It doesn't need nutrient input from outside. Lush and impressive, and looking as though some fisherman has draped the leaves with a net of vines, this rainforest is a living reminder of how ancient Australia must have appeared. Today, only 1% of that blanket of rainforest remains, and most of that is broken up into small, isolated fragments. It's the business of ecologists like Dr. Graham Harrington, director of CSIRO's Tropical Forests Research Centre at Atherton, to monitor the health of rainforest fragments like these and to shed new light on our understanding of how rainforests work. As we climbed a research tower to get up into the canopy, Graham made an interesting point on just how hot it is once you get into the world above the leaves.
You know, those leaves over there, they're really hard and leathery, sort of leaf you'd expect to see in the arid zone. And really, this is quite a hot and arid environment up here. And, you know, down below, you get the impression of how cool and equable the rainforest is. The trees up here are taking all the stress. So it's very nice for the plants and the human beings that are underneath. This particular rainforest type has survived in only 3 tiny fragments of a few hectares each because it is prime agricultural land, probably the best agricultural land in Australia. And so this rainforest type has virtually ceased to exist. And this problem excited me when I came up here. And so a small group of us at the lab at the Tropical Forest Research Centre are looking at how the species, the animals and the plants, cope with this fragmentation. We are particularly working on really large seeded trees. Well, you take this seed, for instance. I don't know what disperses that. Cassowaries possibly could, but they don't, as far as is known. It's poisonous anyway. Now, the only thing that really moves it is that it rolls. Now, I've got a theory that that has been rolling downhill for the last few million years, ever since its dinosaur disperser went extinct. And it has It is only now found on river flats, right at the bottom of the system. Probably in another million years it will have rolled clean out of the system and be extinct itself. Throughout the world, a lot of the rainforest types can only conceivably survive in fragments. That is why it's very important for us to know which are the attributes that are going to make animals and plants most endangered by this fragmentation process, so that we can manage those particular species and make sure they don't go extinct.
Who cares if they go extinct? Why should we worry about them?
Well, I care, and I guess that goes for most people who really think about it. But I think most people, once they understand what extinction means, they do care. It isn't, I mean, you can make practical arguments about the potential commercial value of these things and so on. I think that is a facile argument myself. I think that defeats the purpose of conservation. I'm not a sort of plant liberationist or an animal liberationist, but I do think that if one species on this earth is going to drive everything else to extinction, you hardly have to argue that there's something wrong.
That something is seriously wrong with rainforests worldwide became all too clear when forests in Malaysia, India and especially Brazil came under electronic scrutiny from space. Landsat pictures made the extent of deforestation glaringly obvious. Also strikingly obvious is just how much of Australia is covered by desert. Australia's arid zone has traditionally been thought of as a single habitat, the Outback. But remote sensing data have made it abundantly clear that it's much more complex and subtle than that.
Rather than being a single amorphous landscape, we now recognise a series of levels from which to view the country. At the microhabitat level, we've discovered that even seemingly trivial changes in landform, say a half-metre rise in altitude or a shallow depression, can have a profound effect on the vegetation that grows there. This produces characteristic patterns in the vegetation that can be recognised right through from the microhabitat level to the level of the landscape as a whole.
The traditional way of farming the outback was to measure up the farm, calculate how many stock could be carried by that area of land, then essentially fill up the paddocks with as many sheep or cattle as those paddocks could hold. Not surprisingly, many station owners went bust. This is difficult and unforgiving country. The single most important problem that has plagued farmers down through the years is that not all of the arid zone can or should be farmed. Only a small fraction of each farm can actually support sheep or cattle, so a farm of 30,000 hectares might contain just 10,000 hectares of usable land, and the total stocking rate must be reduced accordingly. CSIRO ecologist Dr. Mark Stafford-Smith has developed a way of bringing all these various factors together using a computer model called RangePack that will hopefully make life a little easier for station managers by taking some of the guesswork out of the decision making.
Now, the sort of project that we're trying to deal with in our RangePack project is to take some of the wide experience and enormous numbers of research results which we've had over the last 50 years in Australia in managing these sorts of areas, but take them from the science, which is relatively incomprehensible and difficult to use for a manager, take them from that into a form which really can be used easily. We're just coming up to a bit of a stream bed here. You might even want four-wheel drive. I'm not sure. It looks a bit sandy.
I might put it into four-wheel drive, I think.
I think I would.
Should be it. Here we go.
Yes, I think this is the really important thing, that producing biological information by itself doesn't actually really provide managers with the tool to help them make the decision. I mean, is this option or that option best? You have to have some sort of measure, and the key one, of course, for most managers is the question of how much money it's going to make. I think the whole Australian thing is a matter of scale and time and the way in which those things interact to make things really complicated. And out here, what we're looking at is paddocks, enormous great paddocks, which are 200-300 square kilometres. You'll see we're just driving through here a bit of an erosion patch, basically, where material's being moved off and being redeposited elsewhere. And that's another element of the complexity of the landscape, in that
What
there are
moves
these
it off?
patches.
What moves
Basically water. Water flowing across here when you do get a big flood. And that's another image, if you like, of the variability through time that we have here. The storms that come and go. So we may have years with really very little rain, and then suddenly a big flood comes in and it moves this whole landscape in one go.
This particular paddock near Alice Springs in Central Australia is possibly the most intensively studied arid zone paddock in the world. It's been the subject of numerous CSIRO research projects for nearly 30 years.
Looks like a spot.
Quite a climb.
Yeah, but it's really worth it for the view when you get here.
It's beautiful, isn't it?
Yeah.
Oh, gee. Let's get this little number going.
Yeah, let's get some wood together.
Okay. So tell me about the paddock, Mark.
Well, out here is what it's all about, really. This particular paddock here has got about 4 water points in. One's just behind us, and there's another one just down to our right there, and another 2 off in the distance, which you really can't see because this is an enormous great paddock. This is 15 kilometres square, and it really is the key of the whole thing, because 70% of Australia is basically like this. 70% of Australia we have to manage at this sort of scale, whether it be conservation areas or pastoral areas or Aboriginal land or whatever. So this really is it. The most important thing in any arid zone paddock really is the water points, because the animals have to keep coming back to those on days like this, or even worse in summer, when they need to drink at least once a day and sometimes more. And whether it's sheep or cattle, they're repeatedly coming back to the water, so you get this focusing on the water points. But then in addition, the cattle, well, all grazing animals in fact, have some preferred types of vegetation which they'll go and graze in preference to others. And so you get an additional sort of focusing effect, a subsidiary of focusing effect on these vegetation types, the preferred ones. In most paddocks, most vegetation types, you get the majority of production off a relatively small proportion of the paddock. And we can look at that on the computer here quite easily, if you like. What we've basically got here is just a little portable computer. And we can easily just set up the model and get it running on here to show you what this paddock out here looks like. Well, what you can see here now, David, is the fence line outline of the paddock that we've got out here, and you can see the water points here. This is the dam just down here in front of us. There's the other 3 off in the distance. And what we can do now, we can put up the vegetation types and look at them, and you can see there the patterns, and you can see this patchy vegetation type just out here going off into the distance. And what I can do is just to use the models which we've got in here very quickly to give us the patterns of usage. And you can see here how as you'd expect, the pattern of usage is basically focused around the water points down here, but on the particular vegetation types that the animals prefer. Now, the critical thing about this is, I mean, any manager I think would know, obviously, that the areas close to the waters are going to have more use. But the critical thing is we can say how much more quantitatively, and that's really important for being able to say how significant is it in terms of if we want to put in another water point to try and even things up, how significant is that?
Speaking of watering points, the billy's boiling. What's in the ammo box?
Well, what's it to be?
Earl Grey.
Okay, that's great. Mark, these computer systems have been applied in various forms right across the country now. Are there any overriding principles coming out of that study?
I think if there's one general principle that we're starting to pick up as we do studies in more and more places across the country is that it's that if one wants stability against drought, if one wants to be able to look after the land, and if one still wants to be economic in the long term, one has to be looking at relatively lower stocking rates and higher per animal production. And I think that's a message that's coming out right across the country.
Any arid zone station manager will tell you just how difficult it is to get it right out here. There are so many factors to take into account, and then there's the weather. Unpredictable as always. The value of a computer model like RangePack is that it allows a station manager to try out several different management strategies in advance, and then to select the one that best suits the local conditions. The model draws not only on satellite data, but on ground monitoring information gathered by researchers like Dr. Margaret Friedel, also based in Alice Springs. Margaret explained how rainfall drives the outback.
You can see every 20 years or so, there's a time when the rainfall for 3 years or so is very, very much above average. And that leads to really big pulses of growth. One of the things that follows from that is that if you've grown a lot of vegetation almost immediately after those rains are over, within about 3 years, you start to get wildfires. Here's this block of fire here, and another very big one here following massive rains we had here in the 70s. The next thing that you can see out of this too is that where we've got information, your peak of animal numbers comes after that again. In other words, they've gone on breeding up. And so your peaks come here. Here's cattle down below, this line here, and rabbits here. So that your peak of animal numbers comes as you're going into your next drought. And so this is a very, very important time for management. You've got to understand your country. You've got to be ready to act at the critical times, because if you're not controlling animals before that time, you're likely to do a lot of damage when that next drought comes in.
The price for getting it wrong is high. Out here, you don't get a second chance. Australian soils are the most nutrient depleted on Earth. So everything, the plants and the animals, are pushed right to the limit. If you stock an area too heavily, the vegetation can't cope, and you wind up with this. What people usually mean when they think of a desert. But that desert is really very much alive, and ironically, the key to that life is a force we normally fear: fire. Fire has long been a part of Australia's desert landscape. From the time 30 million years ago when the continent began to dry out, fires have been started by a range of natural events, the most important of which is lightning. Aboriginal Australians brought with them the simplest of fire technologies, Firestick Farming. It may have been simple, but it was a highly effective game management strategy. So widespread was the Aboriginal use of fire that by the time Europeans arrived, much of the country apparently was ablaze. For a time, every effort was made to put fires out as soon as they started. paradoxically, a new breed of ecologists like Graham Griffin spend a great deal of their time deliberately setting fire to the spinifex.
There are two reasons behind burning in this sort of country. One is to try to control the effect of extensive wildfires, and the other is to increase the diversity of the landscape. Now, the first one, by controlling the extent of wildfires, by going through a country like this and burning it at different times and in different places over the months and over the years, you break up the country with different levels of fuel over a long period of time. And then when the wildfires do come, by lightning strike or by accidental lights by people, they'll run into these patches and eventually be broken up and go out, so that it requires then no management. The other side of it is to provide diversity in the habitat. Once these patches are burnt, after the rains come, they'll grow up and you'll have a flush of edible grasses and forbs that will be very different from this big spinifex. Now that provides a habitat for a different group of plants and animals that make use of that stage.
There's a wide variety of animals out here. Most of Australia's reptiles live outside the rainforests, and they each have their own specific requirements for habitat. More importantly, they all need somewhere to run to, refuges from the worst ravages of fires. Some, like this lizard, don't make it, but they become food for predators like black kites that seem to appear from nowhere whenever smoke signals that a fire has started. Ironically, after 200 years of trying to stop bushfires completely, Europeans are now using patch burn methods reminiscent of those refined by Aborigines over tens of thousands of years. Once again, Uluru is veiled in smoke. Symbol of ancient Australia and a source of spiritual inspiration to Australia's Aborigines, Ayers Rock has a magnetic appeal for tourists. Yulara Village caters to the needs of 250,000 tourists each year. Some pampered by the pool, others preferring to rough it. They all come to see the rock at sunset, and each evening the ancient monolith swarms with visitors. At such a place, the pressure of tourism is intense. The McDonnell Ranges offer attractions of a different kind. The textures of weathered rock, the chance to observe wildlife. The pristine solitude of a waterhole in the evening light. I shared an evening here with a long-standing friend, Dr. Steve Morton, and asked him how tourists could possibly be brought into such a remote place without wrecking it.
Well, I think the way to begin, Dave, is to understand that you simply can't build a bitumen road in here and ship busloads of people in and expect them to enjoy it. Well, in the first place, they'll wreck it. It's undeniable. Too many people in a small, isolated location like this would ruin it. And in the second place, if you get all those people in here together, then the atmosphere of the place will simply disappear. So too many tourists is you know, it's the wrong way to go.
Yeah, I suppose one of the
delights of being in a place like this is that we've got it to ourselves.
That's right. It's magical, this sort of place. So once you've realised that, the next realisation is that the way to go about it is to make sure that your tourist usage of these sorts of places is dispersed. You know, it's a rare resource. There's little patches of these sorts of ponds and moist gullies back in these ridges. And the only way to get people to see them effectively is to disperse that visitation. So that creates another problem. That, what I said doesn't require a great deal of intelligence. It's not very clever. You simply plan ahead. What is difficult in this environment is the very spatial nature of it all. It's huge. These little pockets of moist gorges and waterholes like this one are rare, and they're scattered all over this huge country. So what you need to do is use some form of remote sensing to identify their locations in the first place. And once you've done that, then you can start to plan effectively. And once you know where they are, you can start to go and visit them and to investigate their particular characteristics that you know, each one has peculiarities which mean that it's got to be treated and managed in a different way.
But you're a biologist. You don't work for the Tourist Commission. What's a biologist doing out here, studying tourists?
The answer is that in the future, the major impact on this environment is going to be human visitors. And as a biologist interested in the conservation of these places, in addition to explaining them to people, I'm anxious to ensure that they aren't ruined, not only for human visitors, but also for the plants and animals that live here. It's just not good enough anymore to expect people to come here and point their cameras at a pretty scene and then be shipped back to Alice Springs. What's important is that they get some information about the place, some understanding, so that they go away and tell their friends and their colleagues about the tremendous experience they had based on understanding and not simply on being put in a place and then put back in the bus. So we see that role of providing information to the visitors is as important as making sure that the visitors don't wreck the place when they're here.
In a way, desert like this symbolises the essence of the Australian environment. It's not just endless hectares of lifeless sand, but a complex and subtle ecosystem that is very much alive. The same applies to all aspects of the Australian environment, from the red centre to the rainforests to the Great Barrier Reef. The key to that life is undoubtedly water, and the key to understanding the chain of events that follows the rains has come from remote sensing and computer analysis. Today, we understand a great deal about the whole Australian environment, how the arid zone relates to the woodlands and eucalypt forests, and how they in turn relate to what's left of the rainforests. The picture that emerges is surprising. Far from being a gloom and doom scenario, we have today a sound basis for optimism, an optimism based on understanding. Despite popular views to the contrary, scientists have been working quietly and efficiently to translate the most sophisticated satellite information into systems that really work for the people who live on the land. They're helping improve the odds in the game of environmental roulette. Ironically, the new vision of Australia incorporates many values and perceptions that Aboriginal people have known for millennia. Rather than adopting a siege mentality against the harshest excesses of climate, we now see undeniable value in taking the softly approach, discovering the subtle rhythms of the environment and working in sympathy with them. The special insights flowing from computer-based environmental monitoring offer great hope for the future. If we apply them properly, they'll enable us to put an end to the present crisis of land degradation and usher in a new, sustainable way of life for Australia.